Okay, everybody. We're going to look at section 4.1, which we skipped over intentionally earlier on. And this section is about transforming to achieve linearity. Okay, so we're going to start off with some data here, and then we're gonna talk about how to deal with it. So what I have is some data here, and this is fish age versus length versus weight. And what I'm interested in is finding a relationship. In my case, I'm gonna be interested in this particular case in finding the relationship between length and weight of a fish. Okay, so 1-year-old fishes have a average, let's say, of 5.2 and a weight of 2, and 2-year-olds have 8.5 and 8, and so on. So what I did is I entered this data into the calculator. Here's list 1 is age, list 2 is length, and list 3 is weight. And I went ahead and I graphed it. Okay, so here's my graph of this is length in the x-axis, length in the x-axis, and weight in the y-axis. Now, let's go ahead and take a look at this. So this is a pretty strong relationship. And I'm going to go ahead and graph the relationship and find a least squares regression line. So to do that, first of all, I need to make sure that my catalog, my diagnostic is on. Now this should be something that is already on in your calculator. If it is not, that's how we do it. Okay. Now, I'm going to go to Stat, Calc, and I'm going to do a linear regression of a plus bx. And I'm doing list 2, which is length, versus list 3. Let's leave everything else the same. Okay. Oh. There it is. Okay. And here's my least squares regression line of length versus weight. Okay. What that means is my equation here, I'm going to put down at the bottom, is going to be weight hat equals negative 299.04 plus 25.0.2, let's say, pardon me, times length. Now, typically, again, we go to 3 decimal places. For the purposes of this, I'm going to stick with 2 just to make the explanation a little bit quicker. Okay, so weight hat equals negative 299.4 plus 25.2, and we have an r squared. Remember, this is the percent variability in weight that can be explained by the least squares regression line of length on weight. This is r squared is 0.895, so that's pretty good. 89.5% of the variability can be explained. Okay, so had we not graphed this, though, we might not have a sense that, you know what, this is possibly nonlinear. Now, what I want to do to really verify that is I'm going to look at the residual plot. The residual plot is what we look at just to see how linear the data are. So I'm going to graph the original x values versus the list of my calculator called resid. Now, resid is remade every time you do linear regression. So now if I go zoom stat, I can see very clearly that there's a pattern in the residual plot. What that means is that even though this is a very strong r squared, 89.5% is strong, what it means is there may be a better model out there, a better nonlinear model out there that we can find. Okay, so let's talk about how we're going to do that. That's where the focus is today. Here are the steps we're going to take, and these you should write down. The first step is graph the data. Okay, always graph if you can. Next step is run a linear regression and look at your r value, and more in particular your r squared value. That should be r squared, not r2. Then we look at the residual plot. That's what we just did. And we saw a pattern. If you see a pattern, we're going to try to transform the data by trying one of the following. Now here's a ladder of powers. I don't want you to worry too much about this, but here's the concept. I want us to be strong with the concept. We start here, okay, raw data, power of 1. And what we can do with the ladder of powers is we can try doing one of these different things. So for instance, right now, I'm graphing weight versus length. So my sense is that this is a nonlinear model. So I can try some things. I could try to turn this into a quadratic model. I could try to graph weight versus length squared. That would make it a quadratic model. Okay. I could try to graph weight versus log of L. That would make it a logarithmic model. I could try to graph log of W versus L. That would make it an exponential model. Okay. I could take the log of both of them. That would make it a power model. I could take the square root of L, and that would make it a square root model. So you can see there's lots of different ways we can do that. And so what we do here is instead of coming up with a new function every time we want to do this, instead of coming up with a new calculator function, instead what I'm going to do is I'm going to try graphing the original weights versus the squares of the lengths, or the original lengths versus the logs of the lengths. Sorry, the original weights versus the log of the lengths. And so what this is going to tell me is we're going to get a nonlinear model, but we're going to trick the calculator. The calculator is going to think we're doing a linear model. Let me show you how that works. So let's go back to the data. Here's our original data, and I'll pull up the calculator again. So what I'm going to do is I'm going to make a new list. This list will be L4. And L4, what I'm going to do here is I'm going to try, I've done this problem before, so I know it's going to work out pretty well. I'm going to try graphing W versus L squared. Okay, so I'm going to make L4, list 4, I'm going to make it the lengths squared. So I'm going to make it the same as L2, but squared. Okay, so 5.2 squared, 8.5 squared, and so on. And now what I'm going to graph is I'm going to graph the squared values versus the original W's. So here we go. I'm switching. I'm going to graph the squared lengths versus the original weights. Let's see what happens here when I do that. Check that out. What I have on the x-axis here is length squared, and on the y-axis I have weight. Okay. Now the calculator doesn't know that. Okay, I have to remember that, so that's important. But let's take a look at this. Now it looks like a fairly straight line model. Let's go ahead and check it out. Let's do a linear regression. We're going to go stat, calc, and here I'm going to graph. Remember, I have to keep track. This is hard, so you want to always write this down as you're going. I want to graph my L squareds versus my W's. And now take a look at this. Now what do I have? My new model, I'm going to write it right here next to my old model, is going to be, remember my y value is W, my x value is L squared. So it's going to be negative 81.3 plus 0.57 times L squared, and my R squared here is 0.97. I went from 89.5% variability to 97% variability, 97.8% variability. Okay, my R squared improved quite a bit. Okay, and what I did here was instead of graphing the original x versus the original y, I got tricky and I graphed the original x versus the square of the y. But I didn't have to use the exponential regression, or rather the quadratic regression. Instead, I still used linear regression, but I used linear regression on transformed variables. Okay, and so we end up with an R squared of 97.8. Okay, good. So let's take a look at our steps again. I looked at my residual plot initially. I saw a pattern. I tried transforming my data. Then I repeated the steps. I transformed the data, and I looked at the graph of the transformed data. I ran a linear regression on the transformed data, and I looked at R squared. R squared was better. That's good. So let's go ahead and take a look and see what the residual plot looks like now. We're going to go to stat plot again. I'm going to do my x's versus my residuals. Zoom stat. Now, there's still a pattern, which means there might be a better model out there. So, I could continue trying other different things. I could try a cube. I could try raising it to a different power. I could try taking a log of both sides. There are many different things I could try here in order to try to improve this model. For now, I'm not going to spend my time worrying about that. But in general, the process is to continue to try until you've exhausted everything you can possibly think about. So that's just an important point about this, this kind of work, is that it's imprecise. You continue to work until you get something you think is as good as you're going to get, and that's fine. Okay. So this process of graphing data, running linear regression, looking at your R squared, graphing a residual plot, and then trying a transformation and graphing a linear regression on that transformation, which makes it a non-linear model. That's what's important here. On the AP exam, remember, there's not a lot of problems that ask you to do actual data crunching. So the way they're going to test you on this is not by asking you to do this in a calculator. You don't have to be responsible for being able to do this in a calculator. Instead, you have to understand the process and understand the outcome. Okay, and that's it. Okay, so that's it for section 4.1. Thanks for watching.